morning, one and all. Myself, Sreevani, working as an assistant professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal, Hyderabad. So, in the today's lecture, we are going to learn about one of the important one in the angle which is to be measured in parallel polarization with oblique incidence in electromagnetic waves and transmission lines. Right? So before going to derive the mathematical equation for this Brewster angle, let me introduce first what do you mean by a parallel polarization, how it will be analyzed in the case of oblique incidence. Then, in our continuation, we will derive the equation for this Brewster angle. So Brewster angle, it is also called as polarization angle. Generally, this polarization means orientation of electric field intensity vector in any particular direction in a space is called polarization. Where this Brewster angle is also called as polarization angle and is an angle of incidence at which light with a particular polarization is perfectly transmitted through a transparent dielectric surface with no reflection. So, see this parallel polarization with the oblique incidence means normally the incidences are occur in two different cases. One is normal incidence and oblique incidence. When the wave means if we consider the wave propagating over the transmission is between two different media, medium 1 and medium 2. When the wave strikes the boundary, then means this is the wave called incident wave. When the incident wave touches the boundary or strikes the boundary, part of the wave will be transmitted to the next medium and part of the wave will be reflected back to the same medium. If the reflected wave is combined with the incident wave, then the waves are said to be standing waves or stationary waves. In some of the cases, when the incident wave is completely transmitted to the next case, that is said to be no reflection case. So, with the no reflection case, the angle is to be measured as the angle is said to be polarization angle or simply Brewster angle. So, Brewster's angle, also called as polarization angle, is an angle of incidence at which light with a particular polarization is perfectly transmitted through a transparent dielectric surface with no reflection. Means the instant wave is completely transferred to the next medium then in the medium 2 as the received wave. Then when unpolarized light is incident at this angle, the light that is reflected from the surface is therefore perfectly polarized. As we know that polarization means orientation of the electric field intensity vector and a particular point in the space is said to be polarization. Depending upon this, we have discussed in the previous lectures as a linear polarization, elliptical polarization and circular polarizations. So here Brewster angle or angle of polarization, simply called polarization angle, is defined as the angle of incidence at which light with a specific polarization is perfectly transmitted without any reflection through a transparent dielectric surface. Or in other words, we can say that simply the light incidence at this angle when reflects back is perfectly polarized is called as polarization angle, also as Brewster's angle. Generally, we are representing angle means with the notation called theta, and here theta b is the notation for the Brewster angle. It is measured in degrees, right? So Brewster angle is the also called as polarization angle when the instant wave is completely transmitted to the or becomes a transmitted wave with a no reflection is said to be Brewster angle or polarization angle. Now, the condition for no reflection occurs case, we will define the Brewster angle. So, the condition for no reflection occurs when gamma parallel equal to 0. So, here why we have considered the gamma parallel notation means we are representing this Brewster angle in terms of parallel polarization with the oblique incidence case. So for this, the reflection coefficient is represented with gamma, and parallel related to the parallel, we are representing the notation as gamma parallel is equal to 0. If gamma parallel equal to 0, generally the reflection coefficient gamma is given by, it is the ratio of the reflected wave field strength to the incident wave field strength. There is no reflection means the instant wave is completely transmitted, hence the gamma becomes 0. For a parallel polarization case, we use the notation as gamma parallel, which is equal to 0 case. Means with no reflection, the angle is to be called as Brewster angle or polarization angle. The angle of incidence is known as Brewster angle, and it is represented with theta b. The angle of incidence of the electromagnetic wave from the region 1, and depending upon that, we will be considering as there will be no reflection from the region 2, and all the electromagnetic waves will be observed. Right? So with the no reflection case, under parallel polarization, we used to measure the angle called Brewster angle or polarization angle. Generally, it is represented with theta b. For a parallel polarization, we are replacing incident wave angle theta I by theta b. Now, with the parallel polarization means reflection coefficient is given by gamma parallel equal to, it is the ratio of reflected wave field strength to the incident wave field strength, and it is given by ER by EI equal to eta 2 cos theta t minus eta 1 cos theta b. So previously in general we have represented it with gamma parallel is equal to ER by EI equal to, generally it is represented with in terms of reflected wave angles and the incident wave angles, it is given by eta 2 cos theta t minus eta 1 cos theta I by eta 2 cos theta t plus eta 1 cos theta I. Right? But we are replacing now in terms of now to define this Brewster angle, this theta is replaced by theta b. So gamma parallel equal to ER by EI equal to eta 2 cos theta t minus eta 1 cos theta b by eta 2 cos theta t plus eta 1 cos theta b, which is equal to 0 according to the no reflection which occur in the parallel polarization. Then gamma parallel equal to 0. Right? So if you equate this one, the total equation, the entire denominator term is equal to 0, and we have left out over here in the numerator term as eta 2 cos theta t minus eta 1 cos theta b equal to 0. Now from this we can separate the theta t terms and theta b terms, then eta 2 cos theta t equal to eta 1 cos theta b, where eta 1 and eta 2 are given by intrinsic impedances of the medium 1 and medium 2. Both are representing two dielectric medium only. So eta 2 cos theta t equal to eta 1 cos theta b, and b is the notation for Brewster and t stands for transmitted wave. Right? And I is for instant wave as well as the, and R is for reflected wave. Right? So with the no reflection, we use the notation theta I equal to theta b and gamma parallel equal to 0. Then consider gamma parallel equation, which is to be obtained in the case of parallel polarization with oblique incidence. Then eta 2 cos theta t equal to eta 1 cos theta b. Next, according to Snell's law of refraction, there are two laws in the Snell's laws. One is theta I equal to theta r is called as Snell's law of reflection, and next one is when theta sin theta t by sin theta I equal to epsilon 1 by epsilon 2 or epsilon 2 by epsilon 1, then this is the case. The law is said to be Snell's law of refraction. Right? So depending upon the reflection and refraction, the Snell's proposed two laws. One is Snell's law of reflection and Snell's law of refraction. Now we are using Snell's law of refraction. That is given by sin theta t by sin theta b. See here, instant wave angle is replaced by b, hence it is sin theta t by sin theta b equal to eta 2 by eta 1, which is equal to beta 1 by beta 2. Eta 1 and eta 2 are the two intrinsic impedances of the both the dielectric surfaces, and beta 1 and beta 2 are the two phase constants of the two media. As we know that propagation constant gamma can be written as attenuation constant alpha and the phase constant beta, then here beta alpha be the real term and attenuation constant where beta be the imaginary, and it is said to be phase constant. So sin theta t by sin theta b equal to eta 2 by eta 1 equal to beta 1 by beta 2. Then by cross multiplying these two, then it will be considered as beta 1 sin theta b. Between these two sin theta t by sin theta b equal to beta 1 by beta 2. Now beta 1 sin theta b equal to beta 2 sin theta t. By cross multiplying these two, sin theta theta b is multiplied with beta 1 and theta t is multiplied with beta 2. Now beta 1 sin theta b equal to beta 2 sin theta t. Right? So T is for transmitted wave and B represents Brewster angle. So next, from this cos theta t equal to, in general we know that the formula for the cos theta t in terms of sine, it is given by the root over 1 minus sine square theta t. Generally it is represented as according to the fundamental equations of trigonometric cos square theta plus sine square theta equal to 1. Now from this cos square theta equal to 1 minus sine square theta can be written. Now from this cos theta t equal to root over 1 minus sine square theta. Okay. So in terms of transmitted waves, we are representing it with cos theta t equal to root over 1 minus sine square theta t. Now substitute. See here cos theta t equal to root over. See from these two relations, sin theta t by sin theta b equal to beta 1 by beta 2 or eta 2 by eta 1. So from those two relations, we will consider here sin theta t equal to eta 2 by eta 1 into sin theta b, or in terms of beta 1 means sin theta t equal to beta 1 by beta 2 into sin theta b. We can consider any of these two relations to derive the Brewster angle. So now we are considering in place of sin square theta t, this relation as sin theta t equal to eta 2 by eta 1 into sin theta b. This one we will consider. Now cos theta t equal to root over 1 minus eta 2 by eta 1 whole square sin square theta b, which is equal to root over 1 minus n1 by n2 whole square into sin square theta b. When we consider index of refraction case and we have derived the Snell's law of refractions case, we are replacing all the terms with refractive indexes and phase constants and intrinsic impedances and densities depending upon all the relations we have derived. Means eta 2 by eta 1 is given by here n1 by n2, where n1 and n2 are said to be two refractive indices, and n is given by n is equal to c by b, where index of refraction is represented with n and c be the velocity of light in free space and v be the velocity of the medium in the particular. Right? So now replace eta 2 by eta 1 whole square with n1 by n2. Hence it becomes root over 1 minus n1 by n2 whole square into sin square theta b. Okay. Then from this cos theta b equal to, see, cos theta b equal to eta 2 by eta 1 cos theta t. And cos theta t equal to eta 1 by eta 2 into cos theta b. If we replace all this, then we will consider cos theta b equal to and cos theta t equal to. Here in the reverse order if we consider, and the intrinsic impedances are to be written in reverse order. Now equate 3 and 4, 5 equations. See here in the equation number 3, what we'll have cos theta t equal to root over this thing, and in general the formula is root over 1 minus sin square theta t, and 5 if we consider cos theta t equal to eta 1 by eta 2 into cos theta b. Okay, so From all this, if we equate those three relations with the cos theta t, then eta 1 by eta 2 cos theta b equal to root over 1 minus eta 2 by eta 1 whole square into sine square theta b. Right? So eta 1 and eta 2 are representing here intrinsic impedances of the both the dielectric surfaces as eta 1 and eta 2. Now, eta 1 by eta 2 into cos theta b equal to root over 1 minus eta 2 by eta 1 whole square into sine square theta b. So, to solve the equation in terms of theta b, we just convert, means by squaring on both sides. So, consider both sides square. It becomes eta 1 by eta 2 whole square into cos square theta b equal to root over 1 minus eta 2 by eta 1 whole square into sine square theta b. So here square root gets cancelled, then it becomes, see, eta 1 by eta 2 whole square into cos square theta b equal to 1 minus eta 2 by eta 1 whole square into sine square theta b. Now separate the sine square terms, means we want to express the theta angle in terms of sinusoidals, hence we are replacing here cos square theta b by eta 1 by eta 2 whole square into 1 minus sine square theta b equal to 1 minus eta 2 by eta 1 whole square into sine square theta b. Now separate the two sines or terms and the real terms. Now from this we will be getting eta 1 by eta 2 whole square minus eta 1 by eta 2 whole square into sine square theta b. By multiplying those two in the previous equation, we multiply, see, n1 by eta 1 by eta 2 whole square into 1 minus eta 1 by eta 2 whole square into sine square theta b, which is equal to 1 minus eta 2 by eta 1 whole square into sine square theta b. So after multiplying those two, then we can separate the sine theta terms as well as intrinsic impedance terms. Then eta 1 by eta 2 whole square, and if you take this one into this side, it will become minus 1, which is equal to, and if you take the total term into this side, then it will be eta 1 by eta 2 whole square sine square theta b, then minus eta 2 by eta 1 whole square into sine square theta b. If you take here sine square theta b as common, then eta 1 by eta 2 whole square minus eta 2 by eta 1 whole square. Okay, and from this sine square theta b equal to, from these two relations, we are going to write the sine theta b formula. So sine square theta b equal to eta 1 by eta 2 whole square minus 1 by, in the denominator, we are going to write the total equation as eta 1 by eta 2 whole square minus eta 2 by eta 1 whole square. Right? So by substituting over here, eta 2 by eta 1 equal to beta 1 by beta 2, this is to be obtained according to the index of refraction, which is to be derived according to the Snell's law of refractions. Right? So from this, sine square theta b can be written as eta 1 by eta 2 whole square minus 1 by eta 1 by eta 2 whole square minus eta 2 by eta 1 whole square. So for a lossless media, beta equal to omega root over mu epsilon. So for a lossless medium, how the phase constant become omega root over mu epsilon means, as we know that loss term is representing with attenuation constant alpha. So for a lossless one, we are representing it with alpha equal to 0. How alpha becomes 0 means, according to the propagation constant gamma equation, in terms of all the characteristic wave equations, then it will be given by here root over j omega mu into sigma plus j omega epsilon is the general equation which includes all the wave characteristics. Now from this, so sigma, if you substitute sigma by 0, why sigma by 0 means, for a lossless medium, it is said to be lossless dielectric medium, is also called as perfect dielectric medium. So for a perfect dielectric medium means nothing but perfect insulating medium, this can be sigma, the ideal value of the sigma must be equal to 0. So if you substitute over here sigma by 0, then gamma becomes root over j omega mu into j omega epsilon. By substituting sigma by 0 here, then gamma equal to root over j omega mu into j omega epsilon. Then if you take j omega as out of root, then j omega into root over mu epsilon as the gamma. And we know that the gamma can be constitute attenuation constant alpha and the phase constant beta. So this can be written as gamma equal to alpha plus j beta, which is equal to j omega root over mu epsilon. By equating both sides real and imaginary terms, then real term alpha becomes 0 and the imaginary term beta becomes omega root over mu epsilon, where mu and epsilon are the permeability and permittivity of the medium and given by here along with the operating frequency as omega. Beta be the phase constant and it is imaginary term which is from the propagation constant. Okay, and so for a lossless medium, beta is given by omega root over mu epsilon. So if we substitute beta 1 by beta 2 by these two relations, or eta 2 by eta 1 by beta phase constants beta equations, then it will be sine square theta b equation becomes, see, for a lossless media, eta 1 by eta 2 whole square equal to. So substitute eta 1 by means in general the intrinsic impedance eta also. As we know that in the previous how we have evaluated that propagation constant, from the propagation constant beta equal to omega root mu epsilon has come. Similarly here also now to find the intrinsic impedance of the medium in general wave characteristics, then it becomes j omega mu by sigma plus j omega epsilon under root is the general formula for the intrinsic impedance. Okay, so eta equal to root over j omega mu by sigma plus j omega epsilon, right? So now substitute over here for a lossless dielectric medium or for a perfect dielectric medium, sigma equal to 0, then eta equal to j omega mu by j omega epsilon. By substituting sigma by 0 here, then j omega mu by j omega epsilon is left out. J omega gets cancelled, eta equal to root over mu by epsilon need to be obtained. Right? So now from this eta 1 by eta 2 whole square equal to. So now substitute with respect to the medium 1 intrinsic impedances, this given by root over mu 1 by epsilon 1 whole square into root over mu 2 by epsilon 2 whole square. For the medium 1 it is given by mu 1 by epsilon 1 and medium 2 it is root over mu 2 by epsilon 2. So by substituting these two in this, then root over mu 1 by epsilon 1 whole square by root over mu 2 by epsilon 2 whole square, then square root gets cancelled by multiplying and this becomes mu 1 epsilon 2, and in the denominator also we'll have a ratio and this becomes multiplied factor, then mu 1 epsilon 2 by mu 2 epsilon 1. That is a value which is to be obtained for eta 1 by eta 2 whole square. Now similarly for eta 2 by eta 1. So if we substitute over here eta 2 by eta 1, then equal to root over mu 2 by epsilon 2 whole square by root over mu 1 by epsilon 1 whole square. Here also square root gets cancelled, mu 2 by epsilon 2 into epsilon 1 by mu 1. Now collectively we can write it as for eta 2 by eta 1 equal to mu 2 epsilon 1 by epsilon 2 into mu 1. See, eta 1 by eta 2 whole square equal to mu 1 epsilon 2 by mu 2 epsilon 1. Now the ratio becomes reverse, hence eta 2 by eta 1 whole square equal to mu 2 epsilon 1 by mu 1 epsilon 2. Okay, now sine square theta b equal to. So what we'll have in the previous sine square theta b equal to eta 1 by eta 2 whole square minus 1 by eta 1 by eta 2 whole square minus eta 2 by eta 1 whole square. By substituting those two ratios here, then it will be sine square theta b equal to. Then eta 1 by eta 2 means that value is given by mu 1 epsilon 2 by mu 2 epsilon 1 minus 1 by eta 1 by eta 2 whole square minus eta 2 by eta 1 whole square. So these two can be substituted over here, mu 1 epsilon 2 by mu 2 epsilon 1 minus 1 by mu1 epsilon 2 by mu2 epsilon 1 minus mu1 epsilon 1 by mu2 epsilon 2. Right? So after simplifying this equation, we will be getting the value as c sine square theta b equal to 1 minus mu2 epsilon 1 by mu1 epsilon 2 by 1 minus epsilon 1 by epsilon 2 whole square. How means? See here. Now, by taking LCM between these two and simplifying, see in the denominator we'll have mu2 epsilon over here. Means if you simplify this equation, mu1 epsilon 2 minus mu2 epsilon 1 by mu2 epsilon 1 into, in the numerator, mu2 epsilon 1 into mu2 epsilon 2, mu1 epsilon 2, this one, by, and if you cross multiply 2, mu1 square epsilon 2 square minus mu1 square, mu2 square epsilon 1 square by, in the denominator this term will be obtained. So this and this gets cancelled, means mu2 epsilon 1 and mu2 epsilon 1 gets cancelled, both the in the numerator and denominator, then it will be obtained as here. In the denominator, these two are to be left out, that is 1 minus epsilon 1 by epsilon 2 whole square. In the numerator, 1 minus mu2 epsilon 1 by mu1 epsilon 2. Right? So upon simplifying, in the denominator, we'll have only electric permittivity values are left out. Those two are 1 minus epsilon 1 by epsilon 2 whole square. Right? So upon simplifying this equation, means for a non-magnetic media, we will be assuming here mu1 equal to mu2. Then by substituting mu1 and mu2 by the same value, identically values as mu1 by mu2 or mu2 by mu1, then it becomes sine square theta b equal to 1 minus mu2 epsilon 1 by mu2 epsilon 2 by 1 minus epsilon 1 by epsilon 2 whole square. Now mu2 gets cancelled, then 1 minus epsilon 1 by epsilon 2, and in the denominator if we observe, it will be becomes a square minus b square formula looks like, and if you expand this one, a square minus b square is equal to a plus b into a minus b formula. And a is the value which is given as 1 and b is given by epsilon 1 to epsilon 2. So upon expanding this one in terms of a plus b and a minus b, in the denominator if you observe, 1 minus epsilon 1 by epsilon 2 into 1 plus epsilon 1 by epsilon 2 is left out. And in the numerator and denominator both gets cancelled, then 1 by 1 plus epsilon 1 by epsilon 2 is left out. Or by simplifying this one, 1 by means epsilon 2 plus epsilon 1 by epsilon 2, or this can be written as epsilon 2 by epsilon 1 plus epsilon 2 as given by sine square theta b, or sine theta b equal to 1 by root over 1 plus epsilon 1 by epsilon 2. Right? So see here, sine square theta b equal to 1 by 1 plus epsilon 1 by epsilon 2. To get the value of theta b, by considering both sides square root, then it becomes here sine square root gets cancelled. Sine theta b equal to 1 by root over 1 plus epsilon 1 by epsilon 2 is left out, or theta b can be written as sine inverse of 1 by root over 1 plus epsilon 1 by epsilon 2, or we can write that is as theta b equal to sine inverse of root over epsilon 2 by epsilon 1 plus epsilon 2. Right? So these two are 1 and 2 are called densities of the, depending upon the density of the medium, we will consider the two notations as permittivity values, or for the both the dielectric surfaces as epsilon 1 and epsilon 2. So theta b is called as here Brewster angle or polarization angle, and it is to be obtained in the, finally the mathematical equation for that is given by theta b equal to sine inverse of root over epsilon 2 by epsilon 1 plus epsilon 2, or theta b equal to sine inverse of 1 by root over 1 plus epsilon 1 by epsilon 2. Right? So this is the way what we have discussed in this particular lecture is the when the reflection occurs and when there is no reflection in the medium, and depending upon the reflections and no reflections case, we will be defining two different angles. One is critical angle and another one is Brewster angle, where critical angle can be defined from the normal incidence of a plane wave, whereas this Brewster angle can be analyzed with respect to the oblique incidence in two different cases. One is with the perpendicular polarization and another one is with parallel polarization. Under parallel polarization case, no reflection occurs case, we will define the angle called Brewster angle or polarization angle. Generally, we are representing it with angle is to be measured represented with theta, and here B stands for Brewster. The scientist who proposed the uh, formula for this is called as, depending upon his name, has given Brewster angle. This is also called as polarization angle. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.